the dying giant. That could light up our sky high above us burns a celestial time bomb, a stellar giant so colossal and unstable that its very existence defies comprehension. Astronomers worldwide agree on one chilling certainty: this massive star will explode in a cataclysmic supernova that will be visible from Earth. The haunting question that keeps scientists awake at night isn't whether this cosmic detonation will occur, but when. Some suggest it could happen tomorrow morning. Others theorize we've already witnessed its death throes centuries ago, and we're simply waiting for that final flash of light to traverse the cosmic void and reach our world. When that moment arrives, the explosion will transform our night sky into something unprecedented in human history. But what accompanies such a stellar apocalypse? Could this distant detonation threaten our atmosphere or cripple our satellites? Does this cosmic giant pose any genuine danger to life on Earth? The answers lie in understanding one of the most fascinating and terrifying objects in our celestial neighborhood. The red giant at Orion's shoulder, Betelgeuse, stands as more than just another point of light against the darkness. It represents one of those rare cosmic landmarks that manages to be simultaneously famous and profoundly misunderstood. Most observers have gazed upon it countless times without truly comprehending the monster they're witnessing. Positioned at Orion's shoulder, this crimson beacon glows with deceptive constancy, appearing steady and eternal to the casual observer. Yet nothing could be further from the truth. Betelgeuse pulses with instability, its variability and enormous scale, making it a prime target for astronomers studying stellar evolution's final chapters. This celestial behemoth belongs to an elite class known as red supergiants, a designation that immediately reveals its doom. Its Enki,
staggering size, it possesses only 10 to 20 times our Sun's actual mass. This apparent contradiction reveals Betelgeuse's fundamental instability. The star has become grotesquely inflated, its outer layers stretched impossibly thin like a balloon approaching its bursting point. This bloated condition signals its approaching demise. Stars reaching this evolutionary stage cannot sustain themselves much longer. They consume fuel at catastrophic rates. That characteristic red glow we observe isn't beauty, it's a death shroud. The surface appears cooler than our Sun only because the outer layers have expanded so dramatically that surface temperatures have plummeted. But within its core, conditions have become hellish. The stellar furnace is running out of fuel sources, having already exhausted hydrogen and helium, now desperately fusing progressively heavier elements in a doomed climb up the periodic table. Once iron production begins, the stellar death warrant is signed. Iron fusion cannot generate energy, it consumes it. Without the outward pressure of nuclear fusion to counteract gravitational collapse, the entire stellar structure implodes catastrophically. In a fraction of a second, millions of years of stellar evolution culminate in an explosion of unimaginable violence. This fate awaits Betelgeuse. Not potentially, not theoretically, inevitably. The only genuine uncertainty involves timing. The supernova could occur tomorrow or require another 100,000 years. And because light from this stellar giant requires 640 years to reach Earth, even if the explosion occurred at this very moment, we wouldn't witness it until the year 2665, the mysterious dimming event. Betelgeuse's nature as a variable star adds another layer of intrigue to its story. Like most red supergiants, it pulses and fluctuates, growing brighter and dimmer in cycles that resemble cosmic breathing. However, Betelgeuse exhibits these variations with unusual drama, creating brightness changes visible to naked eye observers over weeks and months. Patient skywatchers can track these fluctuations by comparing Betelgeuse's luminosity to nearby reference stars like Rigel or Aldebaran. This variability is precisely what made recent events so extraordinary and concerning. In late 2019, something unprecedented occurred. Betelgeuse began dimming rapidly and dramatically, not the gradual, predictable variations astronomers had grown accustomed to, but a steep, alarming drop of over 50% in just a few months. The change was so pronounced that anyone familiar with Orion's constellation could notice the difference. From being one of the brightest stars in Orion, Betelgeuse faded to barely ranking among the constellation's top 20. The transformation wasn't subtle. It was visible proof that something extraordinary was occurring within this stellar giant. The astronomical community responded with intense scrutiny. Observatories worldwide, including space-based instruments, focused their attention on this cosmic drama. The Hubble Space Telescope detected compelling evidence of massive material ejection, enormous clouds of dust and gas streaming away from Betelgeuse's surface. Two primary theories emerged to explain this dramatic dimming. The first suggested that Betelgeuse had literally ejected part of itself, explosively shedding massive portions of its outer shell. This expelled material subsequently cooled and condensed into dust clouds positioned between Earth and the star, creating a natural curtain that blocked significant amounts of stellar light. In this scenario, Betelgeuse hadn't actually weakened. It had simply obscured itself behind its own ejected material. The alternative explanation focused on internal changes. Perhaps the star's surface temperature had genuinely dropped due to massive convective disturbances within its structure. Red supergiants are inherently unstable, with internal convection capable of creating enormous temperature variations, brightness fluctuations, and even geometric distortions across the stellar surface. A third possibility combined both mechanisms. Internal instability triggered external ejection, creating a cascade of effects that resulted in the observed dimming. For months, the astronomical world held its collective breath, wondering if they were witnessing the preliminary stages of a supernova explosion. Then, gradually, Betelgeuse began recovering its previous brightness. The star returned to normal behavior, resuming its typical pulsations and variability patterns. However, this episode left lasting implications. It demonstrated that Betelgeuse possesses greater instability and complexity than previously understood. If it could randomly expel portions of its outer layers and dim by half within weeks, then the prospect of sudden supernova detonation seemed less remote and more imminent. Most unsettling of all, if Betelgeuse had actually exploded during the 14th century, this type of erratic behavior might represent exactly what we'd observe in the centuries leading up to the light finally reaching Earth. Final tremors before the ultimate cosmic finale. The light speed time delay. When we observe Betelgeuse glowing in our night sky, we're not seeing its current state. We're viewing it as it existed approximately 640 years ago, the time required for its light to traverse the cosmic distance to Earth. The star we see tonight represents a medieval postcard finally reaching its destination. This fundamental limitation of observational astronomy creates profound uncertainty about Betelgeuse's actual current condition. We possess no real-time information about this stellar giant. The star could have exploded centuries ago, and we remain completely unaware, still waiting for that final message to arrive. This situation resembles watching a live broadcast with a 640-year transmission delay. Every observation we make, every change we detect, every fluctuation we measure already happened when human civilization was fundamentally different. When the light now reaching us originally left Betelgeuse, the Renaissance hadn't yet begun. The Americas remained undiscovered by Europeans, and astronomical understanding was primitive. This temporal disconnect has created unique suspense within the astronomical community. Every unusual behavior, every dimming event, every fluctuation raises the same haunting question. Are we witnessing the beginning of the end, or is the end already over? If Betelgeuse detonated during the 1380s, the light from that explosion would reach Earth approximately now. When it arrives, it won't appear gradually. It will manifest as a brilliant flash capable of outshining the full moon, visible even during daylight hours. At night, this new celestial beacon would cast shadows on the ground, lingering in our sky for weeks or months before slowly fading, The mind-bending aspect of this scenario is that if the supernova becomes visible tomorrow, we won't be witnessing an event occurring in real time. We'll be observing something that concluded hundreds of years ago, finally catching up to us across the vast cosmic distances. This temporal gap renders prediction attempts somewhat futile. Scientists can model probabilities and analyze current behavior, but if the explosion has already occurred, there's nothing left to predict, only the light's arrival to await. Astronomers discuss Betelgeuse in terms of probability windows. Some estimate the explosion will likely occur within the next 100,000 years. While this sounds distant, in cosmic terms it represents an infinitesimal moment. Stars don't remain in the red supergiant phase for extended periods. It's a brief, unstable, dramatic conclusion to an incredibly long stellar lifetime. We exist at precisely the right moment to witness this cosmic spectacle, or perhaps at the exact moment after it has already concluded. Either way, Betelgeuse serves as a constant reminder that our night sky isn't showing us the present. It's a gallery of ancient light, a history museum glowing in real time, where one of those luminous points may already have ceased to exist. The mechanics of stellar death. When Betelgeuse finally reaches its explosive conclusion, the event will unfold according to physics so violent and rapid that they challenge human comprehension. The process begins deep within the stellar core, where the nuclear furnace has been methodically consuming progressively heavier elements, from hydrogen to helium, carbon, neon, oxygen, and silicon, in a desperate attempt to maintain the energy production that keeps the star from collapsing. Eventually, this nuclear ladder reaches iron, and the cosmic game ends abruptly. Iron represents a fundamental dead end in stellar fusion. Unlike Lig-Jahausen, H2 elements that release energy when fused, iron fusion actually consumes energy, effectively extinguishing the nuclear fires that have sustained the star for millions of years. At this critical moment, the stellar core transforms into a dense, iron-rich sphere surrounded by collapsing layers of gas and plasma. Gravity, which the star has successfully resisted for eons through heat and radiation pressure, suddenly achieves total victory. The core can no longer support the enormous weight above it. What happens next occurs so rapidly, it defies human perception. In a fraction of a second, the core implodes catastrophically. The outer stellar layers, no longer supported, collapse inward at tremendous velocity, then rebound violently off the ultra-compressed core. This rebound generates a shockwave of unimaginable intensity that rips the entire star apart from within. From Earth's perspective, this stellar death will manifest as the most spectacular light show in human history. Initially, we'll receive a wave of nearly massless particles called neutrinos, racing outward at nearly light speed. These ghostly particles will pass through our bodies and planet without interaction, detectable only by specialized underground instruments. Hours later, the main event arrives. An explosion of light, radiation, and energy that will suddenly birth a new star in our sky. Except this won't be a star at all. It will be the death of one, blazing with intensity that could exceed the full moon's brightness and remain visible even during daylight. This cosmic beacon won't disappear quickly. Supernovae linger for weeks or months, gradually fading as the ejected stellar material cools and disperses. Telescopes worldwide will focus on this unprecedented nearby explosion, recording every moment and studying stellar death in real-time detail, never before possible. After the visible spectacle fades, something even more remarkable begins. The collapsed core doesn't simply vanish. It transforms into something exotic. If sufficient mass remains, Betelgeuse could become a neutron star, a city-sized sphere so dense that a teaspoon of its material would weigh more than Mount Everest. Alternatively, if the core possesses enough mass, it could collapse further into a black hole, creating an invisible gravitational monster surrounded by the scattered remnants of its former stellar self. This represents the ultimate fate of red supergiants, They don't merely disappear, but leave behind cosmic scars, dense relics that serve as eternal markers of their former existence. When Betelgeuse meets this fate, the entire world will witness the process, like receiving a message from the distant past that has finally caught up with us. Earth's safety in the cosmic storm. Despite the tremendous violence of a supernova explosion, Betelgeuse poses no genuine threat to life on Earth. The key factor ensuring our safety is distance. That same 640 light-years that creates our observational time delay also provides crucial protection from the explosion's effects. To understand this distance's significance, consider that Voyager 1, humanity's farthest traveling spacecraft, has journeyed for nearly 5 decades and hasn't yet reached even one light day from Earth. Betelgeuse sits over 230 million times farther away than this pioneering probe's current position. When dealing with supernova explosions, distance becomes the ultimate safety factor. While these events release more energy in seconds than our Sun will produce during its entire 10 billion-year lifetime, this enormous output spreads equally in all directions. Like an expanding balloon, the energy becomes progressively diluted with increasing distance, arriving at Earth as spectacular but harmless radiation. Gamma-ray bursts represent the most commonly cited potential threat. These high-energy radiation beams could theoretically damage Earth's atmosphere or destroy satellites if they occurred at close range. However, gamma-ray bursts are highly directional phenomena, shooting out in narrow beams rather than spreading omnidirectionally. Moreover, not every supernova produces gamma-ray bursts, only specific types involving massive stars that form black holes under precise rotational conditions. Even if Betelgeuse did generate a gamma-ray burst, the probability of it being aimed directly at Earth is vanishingly small. More importantly, gamma-ray bursts capable of harming our planet would need to originate within approximately 30 light-years. Betelgeuse sits more than 20 times farther away, placing it well outside any conceivable danger zone. Some space-based systems might detect enhanced high-energy particle flows, and sensitive telescopes could register radiation spikes, but nothing beyond their designed operational parameters. Our Sun regularly bombards Earth with solar flares far more intense than anything we'd experience from Betelgeuse's explosion, and we routinely manage these solar events without significant difficulty. For Earth's surface dwellers, the supernova's only noticeable effect will be visual, a brilliant new light source in the night sky. No radiation sickness, no temperature spikes, no atmospheric damage. Just an unprecedented celestial spectacle. The genuine impact will be psychological, cultural, and scientific rather than physical. Witnessing a star explode and watching it evolve over weeks and months would become a defining global experience, comparable to how previous generations remember eclipses, comet appearances, or the moon landing. It would represent living history, the kind you could observe nightly with your own eyes. For astronomers, Betelgeuse's explosion would provide an invaluable once-in-a-lifetime opportunity to study a nearby supernova as it unfolds. No reconstructions, no theoretical models, just direct observation of cosmic violence occurring in real time. We couldn't ask for a more perfect scenario, close enough to witness the spectacle in unprecedented detail, yet far enough away to observe it safely from our front row seats to one of the universe's most dramatic performances. The countdown continues. Here we stand, gazing up at a stellar monster so massive it would consume half our solar system, so unstable it constantly sheds portions of itself into space, so distant that we're perpetually viewing its ancient past, yet so relatively close that when it finally detonates, we'll witness the explosion with naked eyes. Rarely do we receive front-row seats to cosmic events of this magnitude. Even rarer is knowing the performance is inevitable while remaining uncertain about the showtime. This uncertainty transforms Betelgeuse from merely another star into something far more compelling, a silent countdown clock ticking away in space. The explosion might occur in days, decades, or centuries. It might have already concluded hundreds of years ago. Amid all this uncertainty, One fact remains guaranteed. The moment Betelgeuse explodes, it will forever change how humanity perceives the night sky. Not because we'll face danger, but because we'll witness the death of a giant, live, unfiltered, and precisely on schedule, arriving exactly 640 years after the fact. So keep watching Orion's shoulder, just in case tonight becomes the night when medieval light finally reaches our modern world, illuminating our sky with the brilliant funeral pyre of one of the galaxy's most magnificent giants.